Good evening, all of you. So, hopefully, today the net is going to support, and we'll be concluding the chapter with couple of very interesting things. So, we will be focusing on rest of the reactions of your alkyl halides. Let me quickly join you through the session also. Mm, right. So, I am live. Hello, Srivatsan. Good evening. Right. Uh, Great. Let's start quickly. Others will also join in time, I hope. Okay. So we discussed that the main chemical reactions of alkyl halides can be clubbed under three categories, and these three categories are your nucleophilic substitution reactions, followed by elimination reactions, and reactions with active metals. Active metals means very reactive metals like your sodium, magnesium, potassium, right, with them. So lithium, and basically group 1, group 2, and also we can talk about like group 13 and all, but we'll be focusing only on few reactive metals, not all of them. Nucleophilic substitution reaction, we have done it in the general fashion. Today we'll explore its optical aspect. What is the stereoisomerism of nucleophilic substitution reactions from both SN1 point of view and SN2 point of view? How stereochemically it impacts the overall reaction, and what is the relationship between your individual reactant and when the product is formed, how they are all related stereochemically. We are going to focus on that today. Right. Okay, right now I see only one student, no problem. Let's go forward. Okay, so when we talk about stereoisomerism or optical activity, we are focusing on on a monochromatic light. More detail you will study in class 12th in wave optics. So what the instrument that we use is a polarimeter. This whole thing is a polarimeter, right? So what happens here is you have got a source here. One is the source, right, and through which your this is unpolarized light. What is unpolarized light? When your photons can oscillate in all possible directions like this, then we call it unpolarized light, right? Acha. Then generally we pass it through a Nicol prism. It is a special type of prism which is kind of like, it is parallelly grated like this. So for example, a light which is fluctuating in all your photon is fluctuating in all directions, you can think about the gratings, right? So only the oscillation which can pass through it will be allowed. You can see that only the oscillation which is which is parallel through it can pass like this. Rest all will be blocked. So earlier it was unpolarized. Once it passed through it, you can see here in 4 only the polarized one can pass, right? So now it is monochromatic also. So it will relate to only one particular color, chrome, colorful, one particular color, right? Now you have got your compound over here. In this tube you have got your optical compound. So if this oscillation is obtained as it is, if this oscillation is obtained as it is over here, then nothing has polarized, right? The compound is, sorry, not the compound is your optically inactive. But if you see, it enters here like this and then it ends up tilted towards left here. If you take this as the standard, you see it should have been like this. I mean, when it entered, it should have been like this, but it is in this direction. It is in this direction. So that means it is tilting towards left. So right now, since it is tilting towards left, it is bending light towards left. Hence, it is levorotatory. Had it have bent the light in this direction, then it would have been your dextrorotatory. So this is, see, the normal our normal experiences. For example, if you take water, you pass light through it, it should go undeviated, hence optically inactive. So our normal experience is that it should be optically inactive, light should not deviate. But these compounds are capable of bending light either towards left or towards right, which means they are either levorotatory or dextrorotatory. So this new thing is called your optical activity, right? It is as simple as that. This is the overall device in which we achieve such kind of we study such kind of deviations. So these compounds are called your optically active compounds, right? I hope this part is totally clear. Welcome Lakshmi, welcome Tara, good to see you girls, good to see you students. Okay, now how this originated? It was initially reported by Louis Pasteur, right? So he studied them and he said that he studied tartaric acid, right? And he found out that two of its isomeric forms. Why they are stereoisomeric forms? Because they are rotating. They are rotating the overall, just the way we saw the overall light in two different directions. They are basically the mirror images, right? So if it is one isomer, then if you put a mirror over here, you can see that this is the mirror image of this. How? Now you can see that OH is downward. Here it is like this, right? So these two, and there are certain rules. There are certain rules why this can be achieved. So it is levo, left-handed. This is dextro. So these two together, they are called enantiomers. But there are certain rules to decide whether a compound is going to have its enantiomer or not. I mean, it means its mirror image is going to be or optically active or not. There are certain rules for that. That is what we are going to discuss here. We won't go in great detail because that will require a separate class for stereochemistry, stereoisomerism. That will be provided to you in a separate class where we will take previous year's questions from both JEE and NEET also. But right now we'll limit the discussion more in the context of the whole chapter, because in stereoisomerism, why to limit our discussion only to alkyl halides? We are going to involve other alcohols, aldehydes, ketones, carboxylic acids. We can involve other groups also and solve accordingly, right? So they are right now, they are called enantiomers, right? Acha. Now of course, post Louis Pasteur, two new gentlemen came into the picture, your Hoffman and Bellin, and ultimately it was understood that your carbon is tetrahedral, right? Your carbon is tetrahedral. So if you have got like 4 different groups on this carbon, 4 different groups, like this group A, B, C and D. So if such kind of a scenario is there, then such a carbon is totally unsymmetric, right? Such a carbon is totally unsymmetric, and this molecule has got full potential of being optically active. So if you have got a mirror here, then you are going to get a mirror image, then that will be also optically active, right? And these two together will be again called a pair of enantiomers, right? So you can see that here what we have is that when we have got asymmetry about a carbon, right, the whole molecule is asymmetric in nature, then possibility of optical activity increases a lot. 99% it will be optically active, right? And such carbon atoms, they are also called chiral carbon atoms. They are also called chiral carbon atoms, right? Acha. So, I mean, to understand it a little more, I told you there are certain molecules which are very similar, and I mean their mirror images are exactly similar. There are certain rules how we can decide about it. One is all the four groups on a tetrahedral carbon should be different, right? They should not match with each other, not even a single matching. All four are different, so it is a chiral carbon. One is that. And also when you are forming the mirror image, so if you rotate the first image by 180 degree, right? So I've got this thing and I've got its mirror image. So if I happen to rotate it by 180 degree, then also they should not be superimposable, neither when they are put like this, nor when one of them is rotated, then also they should not be superimposable, right? So you can see that if you have got letter A, you know, written horizontally, the mirror image is like this. But if you rotate, say this one by 180 degree, so the moment you rotate it by 180 degree, you are going to have again the same thing. And these two are what? Superimposable. Hence, they are not going to give you any optical activity. Same about this, right? Hexane 1, 2, diol you have got. Now, right now, if you try to superimpose them, then of course they are not going to happen like this. So right now, if you superimpose them, they are not going to happen. But ants are superimposable in any case. Why? Because if you rotate one of them by 180 degree and then you try to superimpose, then also see nothing is happening. So basically, you have got your hand, you take your left hand, imagine a mirror in front of it, right? Any doubt, please let me know, because there's a little abstract concept. So I would like to have questions from you guys. In case you are finding anything difficult, please feel free to ask your question. So can you write yes? So I understand that all of you are understanding right now what we are discussing, right? Can you guys write an yes if you are understanding everything till now? Srivatsan, Lakshmi, Ramaswamy, students, if everything is clear, please write yes. So I'll get the understanding that everything that we have discussed till now is crystal clear. If not, write no. I'll explain that part again. I don't see either of the two. Okay, any case. So I'll proceed now, since you guys have written nothing. So basically what we have is, we have got this, right, as one mirror. Suppose you have got a mirror here. So the mirror image, there is one object you have got. The mirror image of the other hand is exactly like this, right? So now if you drag it over one another, then we see that it is not superimposing. They are non-superimposable. And even if you like rotate one of them by 180 degree and then you try to superimpose, then also the same thing, non-superimposable, right? Oh, it switched off. Welcome, Amuka. Right? Acha, this is how it happens. So right now these two hands are non-superimposable. They are asymmetric in nature. But here what we see in both cases, even for this hexane 1,2 diol, if you turn it by 180 degree, you will get the exact molecule. So they will superimpose. So right now both of them are same molecules. They are not optically active enantiomers, right? Acha. Now let's think about these two identical twins. Let's talk about these two identical twins. Before that, see, if one has a scar over here on the right eye, so the mirror image is going to have like this, right? Okay, left, right, anyway. So right now they are also non-superimposable. So if you see, if these twins stand one behind another, then one scar is in this this side, the other scar is this side, so which means they are not superimposing. Even if you pick one of them, rotate by 180-degree, then also they will not superimpose, which means these two are optically active and they can act as your enantiomers. If mirror is kept in between, they can act as enantiomers. I hope this part is clear. Right. Okay. So you see, in the first picture, this is a plane of symmetry. So if I bifurcate the whole face, then this side is exactly symmetrical to the other side. So that means they are superimposable, right? Exactly same symmetry is there. So one side is nullified by the other side, right? But here it is not so. There is a scar on the left hand side, but there is nothing on the right hand side. So that means they can have enantiomer. Got it? So this enantiomer thing is, I guess, totally clear to all of you. Okay, now as we discussed that whether a molecule is going to be achiral or symmetric. So basically, if I have like this is my carbon and there are 4 different groups, say A, B, C, and this one is again B. So even if you have got one of the group repeated, then also you are not going to get any asymmetry. This will be counted as symmetric. So that's what we have, because when you rotate this, you are going to obtain the same thing here, right? So basically what you have here, you have got this mirror image is here B, and when you rotate say A or C by 180-degree, you will find the exact same molecule. Hence they are achiral or symmetric in nature. So they are not going to have any enantiomer, right? Any optical activity. Okay, on the other hand, now if you see, your D has got one methyl group, one ethyl group. Last time we had both of them as methyl groups. Now what we have got is both of them as different groups, that is methyl and ethyl. So now if you even after having the mirror image, even if you try to rotate them by 180-degree, you are still going to get 2 different non-superimposable molecules, which means they are totally unsymmetric. So you have got a chiral center, or a stereo center. So such kind of molecules only can give you enantiomer's optical activity, right? Okay. Now if you see in these molecules, see these S and R, they are the way how this is called RS configuration. That is how we figure out which molecule, or they are a way of naming them in terms of their appearance of different groups, where all the 4 groups have got different masses. So accordingly, whether if one has got a clockwise rotation or anti-clockwise rotation, we do it. We'll discuss about this in detail later on. These RS configurations, you can have diastereomers and all. We are going to keep things a little simple now, and its technical name. Don't bother much about R and S. It is a way of naming different enantiomers, right? Okay, so basically what we have got, see in this particular molecule, on one side you have got ethyl group, this is ethinyl group, right? Then you have got methyl molecule, methyl group coming out of the plane, and hydrogen going inside the plane, right? So if you put a mirror image over here, what you get, right? It's a similar thing. These two remain same while these two interchanged as their cell group. So that means they are, if you try to superimpose them, they are going to be different. Even if you rotate one of them by 180°, then also they are not going to superimpose. So these two are enantiomers. And one thing is very important, all the properties that we have got, like melting point, boiling point, various physical properties, they are same for both the enantiomers. So these two are going to behave in similar fashion as far as any physical property is concerned, right? So I hope things about enantiomers is quite clear now with all of you, right? Two things: non-superimposable mirror images, and two, presence of chiral carbons, right? And third thing, their physical properties are identical, right? Okay, so some of the notations which we'll be using throughout are this plus and minus stuff. That means plus means what? Dextro, negative means levo, clockwise, anti-clockwise. And in terms of alphabets, we can also use D and L, where your plus is similar to D and minus is similar to L, right? And if plus and minus is kept together, right, or DL is written together, right? So these two refers to a racemic mixture. That means where both dextro and levo part is present in equal amounts, so they will nullify each other's rotation, optical rotation, and ultimately the mixture that you got is optically inactive, known as racemic mixture. So what is a racemic mixture? Racemic mixture is obtained by equal amounts of dextro isomer and its levo isomer, and they simply cancel out each other's optical activity, and hence the overall mixture is optically inactive. Such a molecule is called, such a mixture is called racemic mixture, right? Okay, next, there is something called diastereomer also. So when do we get a diastereomer? See, in many molecules you have got only one optically active carbon or one chiral atom. But if you have got more than one chiral atom, that means two chiral atoms or more, then they are referred to as diastereomers. Any molecule, an organic molecule with more than two or more optically active centers or chiral carbon atoms are known as diastereomers, right? So what happens in diastereomer? You get more than two optically active compounds. So here's the example. Here, if you see, since these two OH are coming out of the plane, so when you use a mirror, then you get a new molecule with these two OH going inside the plane. So basically they are both non-superimposable images, right? Acha, but they are exactly opposite mirror image, but there is a third possibility also, which is called mesotartaric acid. Now if you see, then this is neither a mirror image of one nor of two. Since they are not mirror images, so then they are simply diastereomers. So relationship of third structure with both 1 and 2 is that of diastereomer, while that of 1 and 2 is of enantiomer, right? And this very important property that diastereomers do not follow each other in terms of physical properties. If you remember, we just discussed that optically active enantiomers are same in terms of their physical properties, hence differentiating them is very difficult. But in case of stereoisomers, then even their physical properties are different as far as their other isomers are concerned. I hope till this part everything is very much clear to all of you, right? Okay, now we enter the stereochemical aspect of SN2 mechanism and that of SN1 mechanism. So if you remember, we talked that in SN1 mechanism it happens in multi-step. Why? Because in the first step, which is your rate determining step, bond breaking happens and formation of carbocation takes place. Now it in itself, it's quite a slow process, right? So that is your rate determining step. So it depends on only the alkyl halide part. It is independent of the nucleophilic part. But in case of SN2 mechanism, your concentration of both nucleophile and that of the alkyl halide matters. They both interact with each other and hence they are part of the rate expression. So rate of reaction depends on both concentration of the alkyl halide and that of the nucleophile. So right now what you are seeing is that this is a secondary molecule, secondary alkyl halide, and nucleophile is attacking it. But see where it is attacking. It is attacking at the rear side. It is not coming from the side where your halide is present. So it is coming from the rear side. So once it approaches the carbon, these three hydrogen R1 and R2, they will straighten up, right? So this is like one single plane, and both nucleophile and halide, they are on opposite sides of this plane. While one is attaching itself, forming a better bond, your halide ion is withdrawing itself. It's snapping its ties with carbon. So what is going to happen after some time, when this transition is complete, your nucleophile would have attached the way it should with the carbon atom. A proper covalent bond is formed, while X has withdrawn its electron and it will move out of the system, right? So but right now, since carbon has got only 4 bonds, it should again go back to its your sp3 hybridization. That's what the rule says. And therefore you see that the 3 hydrogen and 2 alkyl groups, 3 groups were all tilting on the left hand side. Now they are forced to go on the right hand side, and they will remain over there till the time nucleophile is attached with carbon, right? So this is how your nucleophilic substitution reaction can be accounted for as far as your SN2 mechanism is concerned, right? Okay, now further, if we talk about SN1 mechanism, in SN1 mechanism, basically you are removing the nucleophile first, right? And sorry, in nucleophilic reaction, basically first you are removing the halide part, and once it is gone, you have got, like in the first step, you have got Rx, and it's quite slow. Your carbocation is left and your X has gone out. So this is what you get in the first step. In the second step, the nucleophile can attack this, because carbocation is what? It is sp2 hybridized, hence it's a triangular plane. So whenever there is a triangular plane, so if you draw a plane like this, right, something like this, so obviously the nucleophile is going to attack either say from here or from here, right? So that means your nucleophile can attack from the either side. So depending on from which side it is coming, so you can see that on the right hand side your nucleophile is present exactly at the same position where your halide was X was present, while in case of your left hand side product, your nucleophile has come exactly at the opposite position where earlier Cl was present, right? So these two products are formed almost in equal amount because probability is same for both of them, right? It's not that one is dominating the other, and hence here what you get is it has retained the position of your halogen. It has retained, right? While in case of inversion product, the nucleophile has come exactly from the opposite side where hydrogen is even if hydrogen was there, it was projecting on the different side, and now it is on the different side, right? So this whatever, optical activity of this compound in, suppose if it is D, then it will be L, and since both of them are equally formed, the probability favors both of them, so equally formed, so we are going to get a DL mixture of alcohol, which means it is a racemic mixture, cannot be, it is a racemic mixture, and hence it cannot be separated to start with. You are going to get a racemic mixture, equal amounts of both product A and product B, right? I hope this part is clear. Okay, so after this part, next part is very important, your stereochemical aspects of SN1 mechanism. So when we are talking about SN1 mechanism, see, this is what we are talking about: secondary butyl atom. So of course the hit can be both from this side and this side. So of course you are going to get either this let me put it this side. So it will come in this direction, your nucleophile, right? I should have drawn it another way, but doesn't matter, dono hi banega. So right now you see, as far as this is concerned, it's the same thing. So there is retention, and in this case it is exactly opposite the way it was present initially. This is your inversion, right? So retention and inversion both takes place in SN1 mechanism. So equal amount of both are formed. That means one will be obviously levo and the other is going to be dextro, and vice versa, and they will all, both of them will nullify each other, which means ki in this case we are not going to get your desired product. Okay, I hope this much part is totally clear, right? We are going to get a racemic mixture, not the desired individual product the way we got it in SN2. Here it is a racemic mixture, right? Exactly the same thing that you see here, inversion and this. So I wrote it here. Yes, I should have written it in the other part. I'll remove it from here. Right. So what we are getting is, we are getting a racemic mixture. So these two are enantiomers of each other, formed in equal amounts, and that's what we get always. Fine. So this part is totally clear, I guess. Okay, now let's do a question. An SN2 reaction at an symmetric carbon of a compound always gives. So you have got four options. So which one do you think is correct? If you have understood what we discussed last time, I think this should not be difficult for any one of you. So try to answer this. So as we discussed in SN2 reaction of an asymmetric carbon, chiral carbon, it is always, it is always a bond inversion. That means if you start with plus, you will have minus. If you start with minus, you'll have plus. So it is complete bond inversion. So only the fourth option says a product with 100% inversion. So therefore our answer should be the fourth option. right? Yeah. So this is your right answer, the fourth option for SN2 mechanism, right? Okay. Now, I mean, very important aspect of rearrangement reaction, especially taking place whenever your carbocation is involved, because in SN1 mechanism, carbocation is formed, right? So I mean, you think about a particular product, but you end up getting something else. So to understand that, what we have got is this hydride shift, and there is something called methyl shift, right? So basically a rearrangement takes place a lot of time. So a lot of time your what you want with as a final product is not what you get, right? Instead you get something else. Why that something else is happening? That is why to understand that, we need to understand this hydride shift or methyl shift, right? See, now in case of carbocations, we know that the stability order for carbocations is simply tertiary, greater than secondary, greater than primary. So that is what we know, right? Now what happens that, this is a primary carbocation, you see, and this is a secondary carbocation. So obviously primary carbocation is less stable. So in if the energy provided inside the solution is sufficient enough, then one of the secondary hydrogens will simply get transferred here, right? So this transfer is hydride shift, which we also denote as something like this. This is a sign of your hydride shift, and so this hydrogen shifted, this green bond line hydrogen shifted from the second position to the third position, generating a positive here. So from primary carbocation you obtain a secondary carbocation which is more stable in nature, right? Okay, in the similar fashion your alkyl shift may take place, right now you have got like 3 alkyl groups on the left hand side to start with, and this secondary carbocation, which is supposed to be very stable, it starts its reaction. But the end product, what we see always is that, there is a methyl shift. So methyl group will leave this carbon and come to this carbon. So this is your methyl shift. So you can see that this is over here, and from here it has moved in this direction. So there's a positive charge now available over here. So now if you react it further, then bromine will attach over here, right? So this is how your hydride shift and methyl shift takes place. Why this is very important? Because sometimes you have to keep in mind that what kind of product you are going to get, and it may be not your regular product as expected, but rather something else because of this shift, right? Okay, now so let's see what is happening, how SN1 is coping up with your alkyl shift, because I said that it involves mainly carbocations, and carbocation is what you are dealing with, right? So what is happening when you are treating this compound, then chlorine is taken out. See, chlorine is taken out, and you should have got your first carbocation over here, right? So once it is obtained, you see that this carbon positioned at 2 position is what? It is secondary, and it is transferring from position 5 to 2. So basically with this shift, chlorine has gone. After chlorine has gone, this has come in here. See, now you have got your carbocation in this side. So ultimately what happened, your desired product is not what is formed, because this carbocation is more stable than any other possible combinations in this arrangement, and hence this is going to form your 2-methyl propane 1 2-methyl propane 2-ol, but at the same time if OH again attacks here, since it is there in the solution as an aqueous solution. So what is going to happen? It is going to deprotonate it. It is going to deprotonate it, and by which this whole molecule will be stabilized. Right? I hope this whole mechanism is quite clear to all of you. Acha. Now, how your ring expands. This is another example of how your ring expands. So you can see that in this particular molecule, from the second position, your chlorine escapes, leaving behind a carbocation. This carbon is not very stable right now. Not very stable right now. Why? Because the ring has become smaller. Ring has become smaller. From become smaller in the sense means 4-membered ring has got a lot of stress, lot of strain. So because of that, it simply, the third carbon moves from its place and joins the second carbon. That's why from 4-membered ring, now you have got a 5-membered ring, right? A 5-membered ring यहाँ पे. So that's how this cyclopentane is formed from cyclobutane. So this clearly gives you evidence that carbocation atom, if not checked, it will rearrange itself into different arrangements. Then further compound formation is going to become difficult, right? Okay, now let's try this one. What do we have? We have this with alkoxide, and what is going to be your major final product? So see, since it is an aqueous condition, what is going to happen is this chlorine will be replaced, and there will be a positive charge on CH. So what is going to happen is, fine. So what is going to happen is, in presence of aqueous KOH, protonation is going to take place, and ultimately, sorry, this was Cl. So what happens in aqueous solution? Cl minus will depart, and there is a positive sign over here. So now what happens that, this carbon is a 5-membered ring, and it sees a potential for itself if it can expand from here to this carbon, right? So if this happens, what is going to happen? This is the way I've discussed, right? So if this happens, what is going to happen is your ring will expand. Right now it is 5-membered ring. From there, when it expands, it will become your 6-membered ring. Right? So now your OH is, oh, I'm writing OH beforehand, which should not be the case. So you can say that now after this, your OH will come over here. So this is only present in 4th option. Hence your answer should be 4th. Right? So basically your ring expansion from 5-membered ring, it became a 6-membered ring. Why? Because your 6-membered ring is always more stable than your 5-membered ring, right? So this is your answer. Now we come to your normal elimination reactions. Why? How it takes place? See, elimination reaction takes place through 2 mechanisms. Just like SN1 and 2, it also has got 2 mechanisms, E1 and E2. two, that is your unimolecular and bimolecular, depending on number of reactants that is getting involved. But what happens over in overall manner here is that from the alpha carbon your halogen goes out, and from the beta carbon your hydrogen is snatched by a strong base, right? So therefore you get an alkene. So this is what happens in case of your elimination reactions. We get alkenes, right? And also your stronger reagents are used because, or stronger base is used because ultimately a hydrogen has to be extracted from the carbon chain, right? So how it can be done? So you can see that yahan pe. So basically what happened, see, now this is your Sadzeff rule, right? So basically you are removing this bromide, and either the hydrogen at the right hand side is removed or the hydrogen on the left hand side is removed. So either double bond is towards the, in this particular case, towards right, the terminal carbon, or interior to it. So you see that since more than one beta hydrogens are present, so more than one product can be formed, either this one or this one. But you see that this is minor and this is major, and generally we are concerned about major product only, and this pattern is seen throughout. That's why we talk about this rule, right? So basically what happens here, that you know, for elimination, whichever carbon has got, after formation of the alkene, more number of alkyl groups present on the double bonded carbons, that is always more stable than any other isomer. For example, see, either you can have something like this, R1, R2, say R3, R4, it could be same also, but say these are the 4 different groups. Then you can have like something like this, right? So out of these two, the first one has got 4 alkyls present around the double bond, the second one has got only 3 alkyls present around the double bond. So if you remember something from the last year, there was something called GOC, right? And in that, there you had studied something called hyperconjugation. So as far as hyperconjugation is concerned, in hyperconjugation, more the number of hyperconjugated structures, more the stability. So if all these are say methyl groups, then you have got 12 hyperconjugated structures, and in this case there will be 9 hyperconjugated structures. So this structure is more stable than this. So simply we can say, more the number of substituent alkyl groups across double bond, more the stability. So out of these two, this is more stable, this is less stable out of these two. So it has got like 81% formation, this has got 19% formation, and it is only not for these two. In every case the same rule follows. That's why Sadzeff rule is quite important, right? I hope this part is clear. So as I was talking, you have got 2 types of mechanisms, E1 and E2. Again, the mechanism describes how the same reaction can have a unimolecular reactant or a bimolecular reactant present in the rate expression, right? So in case of your E1 mechanism, unimolecular mechanism, see, the whole reaction takes place in 2 steps. In the first step, your base, your living group goes out, leaving behind a carbocation, right? And then in the next step, the beta hydrogen is removed by the base and this bond line moves inside. So this happens very fast. So in this only one compound is involved, hence it is E1 or unimolecular reaction, right? And in the next case, what we have in case of E2 mechanism, both your base and your reactant is involved in the same group. That means it happens simultaneously. Here it happens step by step, but there it should happen simultaneously. So you can see that while X is going out, it's your leaving group, and it is therefore forming trying to form a carbocation, but it happens simultaneously. Your hydrogen goes out, and in place it is snatched by the beaker, and therefore this double bond formation is very easier, and it takes very less time in comparison to even mechanism. So this is how it happens, right? So I hope it is totally clear till now. Acha, let's have some examples here. What do we have? We have the major product of the elimination reactions. They are talking about elimination reaction. That means the condition is alcoholic in nature. Remember that. So basically, if you remove this and if you talk about the major product, so as far as the major product is concerned, this bond is going to form at a position where you have got more number of alkylated groups. So as far as the major group is concerned, so you have got this thing. Right? So you have got chlorine removed from here. So you have got butene, but butene as the major product, because we have been asked about the major products only. I hope this example is absolutely clear, right? In the next question, you have got a fluorine here. So you can have a double bond. So basically you can have a double bond over here. You can have a double bond over here. But if you see, if you put it in the lower part, then only 2 alkyl groups will be formed. But a double bond present in the upper part, then you have got 3 alkylated groups present across the double bond. So the major part is 3, not 2. So you are going to have it like this. So you have got a CH3 over here, CH3 here, CH3 here, and CH3 here. So that means what we are going to have is, this is the major product. The lower one is not going to be major. Why not major? Because right now you can see, as we discussed again, time and again, across the double bond you have got like 3 alkyls. So more the alkylation, more the stability of the formed alkene, right? Acha. Now in this case, there is another aspect which is highlighted here. You see, Br can, when Br is removed, it can go from this hydrogen also or this hydrogen also. So either you can have a double bond over here or on this direction. In the lower part, see what happens if you put it here, then 2 double bonds are totally isolated, totally away from each other. But if you put it in the upper part, then there is conjugation, double bond, single bond, and double bond. So whenever there is a conjugation, there is a large charge dispersal, right? So hence it brings automatically more stability. So therefore the major part in this particular case is going to be, it is already there. So when it is done, it should go from here. This should be your major product. All of them have got alcoholic conditions. That's fine. Fine. So I hope this part is totally clear to all of you. Okay, next comes your reactions with metals. So when you react them with metal, what do you have got? Magnesium. This is formation of Grignard reagent. So basically the common reaction is, you have got Rx, you take magnesium, and with magnesium you do this reaction in dry ether, magnesium gets in between, you have got RMgX, right? So this is a general formula for your Grignard reagent, and the main USP or main benefit of this reaction is that this magnesium and carbon bond, it is partially negative, it is partially positive. That means you can have a generation of carboanion. You can easily have a carboanion over here. Now generation of carboanions is very difficult. Carboanions is very difficult. So this is one method by which you can have carboanions. And presence of dry ether as solvent is very important, right? Why is it very important? Because without this solid form is going to explode if not handled properly, and therefore it is going to be always a danger for the lab chemist, and hence we always prefer to use your ethereal solutions, right? So rest questions and further discussion that we are going to do will be done in the next class, right? So here we come to the end of the class. I hope you have understood whatever we have discussed today. It was a little on the higher side, and any doubt, any discussion that you want to have, please put it there in the comment box. Our team, we are going to look into it, and definitely we are going to get back with your answers. So please use the recorded video well for your revision. Attempt questions from here, look into the assignments, and see you in the next class on Monday, right? So take care. It's goodbye from Rahul sir, your chemistry mentor, right? Bye guys.